So now I will introduce marked point processes. So they are derived from point process itself. So given a point process, if each point of point process has a random variable qi associated with it, then the new object is termed as marked point process. So it is like you have points in the point process, and for each point you assign a mark or which is a random variable, just a random variable. So every point xi has its own copy of random variable qi. Then this new point process with the marks is known as mark point process. And this associated random variable is termed as the mark of that point. And we can extend this to say that instead of random variable, you can have random vectors, random processes, or random field associated with each point. So if there are n points in the point process, there will be n marks. Okay, so that is we can say that without knowing how many points are there, we cannot assign marks. So marks are always given the point. Once I know the point, then I will define it. Okay. Sometimes the distribution of Q does not depend on the location. It is same for all marks. Then points are said to have identically distributed marks. Okay. Sometimes they have different distributions, and it can depend on locations also. Second thing we notice that mark is always associated with this point. Okay. So first to define mark, I need to have the point, this location, then only I can define mark. If I just say qi and without having any I or xi, then that does not mean anything. And second thing, because of the association, when we move the point, the mark must follow the point. Okay. So it's not like you suppose there are 2 points. Suppose there are points on the integer location, like x equal to 1, x equal to 2, x equal to 3, and then you move it. So the point at x equal to 1 moves to point equal to x equal to 2. Okay, and then point at x equal to 2 moves to x equal to 3. So the mark of x equal to 2 point also moves to the new location 3. It's not like that the mark remains same and the point who moved from 1 to 2 will have that mark. Okay, so marks are associated with point and they move when we move the point, or we translate or shift the point process, or rotate the point process. So consider a point process where each point xi represents a person located at this location. And now suppose each point now carries a ball. So this is a point process, and each point now carries a ball which can be either blue or black according to a probability distribution. Okay. So suppose the color of the ball here is the mark of the point. So let the probability of ball being blue is 2 by 3 and black is 1 by 3. So in this realization, we have 15 balls, and on the average, there are 5 black balls or 10 blue balls. But again, it's random, so you cannot guarantee that there will always be 5 or 10, but these are on random distribution. So these balls are marks, and when you move the point, the ball moves, the color of the ball moves with the person. Another example would be let xi be a point process, and so sorry, the formally we define it. Let phi equal to xi be a point process in Rd. Associate a random variable mi, which belongs to Rl. So there is a random vector actually here, and with each point to get the point process. So here you can see the phi dash, actually each point is a tuple of xi and mi. Okay, so this phi dash is the marked point process. And phi is where the points are coming is known as the underlying point process of phi dash. So another example can be a point process is defined as a location of transmitter. So each point is made from xi comma yi, where xi is the x coordinate, y is the y coordinate of the ith point, and the location total coordinate belongs to r square. Now, if I associate height of transmitter to each transmitter, then that will be the mark. So the mark of the ith point located at xi comma yi is hi. So the new mark pointer will be written as tuple xi yi hi, and that will be in R3 or R square comma R. Okay, and of course HI can have some restrictions that HI can only between 3 to 5 meters or something like that. So in that case, you can also say that this is R square cross 3 comma 5. So it's like a plane, and but in one dimension, so it's like a cube, uh, which is extended infinitely into in two dimensions. So if we move base station R or change the origin to any other point, the height of the base station of ith base station will not change. So if we change the origin, the coordinate will change, right? And the base station will move to new coordinate, but the height of that base station will remain with it. Okay. So the ith point will always have hi height. Okay. And its coordinate will change according to the translation. Okay. Similarly, instead of height, you can have power as the base station mark also, which will denote the power or transmit power of the ith base station. Okay. So in that case, the example would be there's a location of base station is xi, and consider set of n base station and assume each base station has its own transmit power, which is a random variable. So power has uniform distribution from 20 to 40 dBm, suppose. Then this xi comma pi with that will make the mark point process also. Okay. And again, with the movement, the power of the base station will not change. And not just one random variable, you can associate more than one random variable as marks. So here P and Hi both can be the Markov point. So in that case, it will be Xi comma Pi comma Hi, and here the mark is actually Pi comma Hi, which is from R square. Okay, so total point process will become from R4. So how do we write down the measure equivalent of this new mark point process? Right? Remember, the point process can be represented in terms of set of points or in terms of a random measure. So as a set of points, marks can be represented, sorry, the mark point process can be represented as tuple, which has coordinate and the mark. And but for measure representation, how can we write this? So the equivalent representation by random measure would be in the following format. So the new point process, remember, it is suppose the points are from RD and the marks are from RL. Okay, then the new point process would be in RD cross RL. Okay, because if we look at the tuple, the first tuple is from RD, the which denotes the coordinate, and the second coordinate is from RL, which denotes the mark. Okay, so I take a set in RD cross RL as A cross K. A is a subset of RD and K is a subset of RL in the mark space. Then total number of points in this set, okay, which I denote as random measure. So the measure of this set is equal to how many points are there in this set, which is equal to summation over all points of phi dash. And then you check that xi belongs to A and mi belongs to K. Okay, so total number of points in this set are equal to number of points which location in A such that their marks are in set K. Okay, so again, just to recall, A cross K is the Cartesian product of two sets A and K. So if you have a point in AB, A cross B cross C cross D, A comma B cross C cross D, C comma D, then it means the first coordinate is in AB and the second coordinate is in C. Okay, that is the Cartesian product. So similarly here, A cross K means the first coordinate is in A and the second coordinate is in K. And this basically tells you how many points are there in A such that their marks are in K. Okay, and this this is a measure of A cross K. And this is a random measure because depending on the points and the mark, the number of points will change. Okay, and from this, if I know exactly for every possible set A and K, how many points are there and where their marks are with such marks, I can uniquely determine the location of each point and their mark. Okay. Now, if you take k equal to RL, then it is equivalent of saying that how many points are there such that their marks are in RL. And of course, the second condition is redundant because the marks are always in RL. So this just means how many points are there in A. So this is equal to phi A actually. Okay. So the number of points which are in A says that their marks in RL is nothing but the number of points which are in A. So this is phi. So if I take a smaller k than RL, then of course phi dash A cross k should be less than phi. Because some marks points will be there whose marks are not in that k. So total number of points which are in A cross k will be less than total number of points in A without any conditional mark. Okay, so let us take an example of that. Suppose there is a base station with height as marks, and so this point process xi comma hi is in R3, where R square xi is in R square and hi is in R. So it is on R square cross R. So first space is the coordinate of point space, second is the mark space. Now if I take a cylinder, uh, B0 comma 1, which is ball at the origin with radius 1, cross 2 comma 5. So it's a cylinder which has a circle uh, at the bottom of radius 1 around the origin, and it has 3 meter height from 2 cross 5, 2 to 5. Okay, and then I ask what is phi dash c? So phi dash c would be nothing but how many points are there which are in this cylinder. Okay, and remember the first two coordinates are location and this is mark. So this basically means how many points are there such that their location is in this ball, in this circle, and their height is between 2 and 5 meters. Okay, this is actually 2 and 5 meters because this is 2. So how many points are there which are located in this circle, and their mark and their height is between 2 and 5. Okay, and from this we can also this is the randomly definition, and from this I can compute the intensity measure for the mark point process. So it's a joint measure on the points location space and the mark space. So this is known as the Campbell-Mathis measure, and which is defined on the RD cross RL as the mean number of points in A cross K is equal to expected of summation over all tuple of the indicator xi belongs to A and mi belongs to A. Okay, so you go to each point and ask, are you in A and is your mark is in K? If they say yes to both questions, you add that point. And total summation, total number of points which say yes is gives you total number of points in A cross K on the average. Okay, so this denotes the average number of points who lie in the set A and have mark in the set K. Again, you can show that if you replace K to RD, you will get C A cross RD, and that this second condition will be redundant. So you just get total number, mean number of points in the set A, which is lambda of A. As I said earlier, the mark point process in RD with marks in RL can also be seen as a point process in RDL, T plus F. How? Why? Because when I have a mark xi and mi, I can combine them into a single coordinate xi comma mi, and that will be in L plus d dimension. And these are also points in this dimension space, so they can also be seen as a point process. So the new point process, which is a mark point process phi tilde, is also a point process in the space RD cross RL, okay, or R T plus L. So let us see an example. Consider a two-dimensional process xi with uniform density lambda. Each point xi is represented by two coordinates xi and ya, where xi is the x coordinate and ya is the y coordinate. So you can also represent this two-dimensional to an equivalent one-dimensional point process phi dash with the location as the xi value, as coordinates as the xi value, and ya as their marks. So xi is the location of the ith point and ya is the mark of the point. So here the mark space will be in also one dimensional and the point space is also one dimensional. So the question we can ask is how this representation is different. Is this new point process same as the conventional point process or something different? Is this uniform? Is this locally finite? So let us see one of few of these questions. First is this new derived process may not be simple even if the original one is simple. So why? Because they may have multiple points at the one location. So if you consider suppose two-dimensional point process, original one, you can expect if it's simple, you can expect no 2 points have the same coordinates. Okay. So if one point is 1, 2, second point cannot be at 1, 2. But there can be points at 1, 3 or 1, 5. So one coordinate, one I suppose x-axis coordinate can be same in 2 points. Okay, but the second coordinate would be different, or the second coordinate is different and the first coordinate is second coordinate is same and the first coordinate is different. That is possible, but for point process to be simple, two points cannot have both coordinates same or all the coordinates same. Okay, but when we have this equivalent one-dimensional point process with one-dimensional mark also, then you can say it is not simple because 2 points can have same x coordinate. Okay, for this point process to be simple, we have to make sure that no 2 points have the coordinate, all the coordinates same, and there is only one coordinate. So it's necessary that 2 points does not have the x-axis coordinate same for the point process to be simple. But we know that in the original point process, that is not the condition. One coordinate can be same, both coordinates will not be same. So the derived point process or the equivalent point process in one-dimensional mark is not a simple one. Okay. Uh, of course, then you can at least be sure that if the original point process is simple, then each of these points, okay, if they have same coordinate, then they will not have the same mark. They will have a different. Okay. Second thing, this new process may not be locally finite, right? So what is locally finite? Locally finite means if you take a finite set, number of points in that finite set will also be finite. So if I take this equivalent one-dimensional point process, and if I ask, so this is a one-dimensional point process. So the interval here would be one dimension. So one-dimensional interval will be, for example, a comma b. It's a bounded set. And so how many points are there in this set? So since there is no restriction on the mark, the second coordinate can be anything, which is the second coordinate, yes, mark. So when I am counting how many points are there, there is no restriction on mark. All the marks will be counted. So all the points with whatever marks they have, if they lie in this interval, they will be counted. Okay. So the points to lie in this coordinate, the x-axis coordinate should be between A and B. Okay. And the y coordinate can be anything. So all the, if I think from the original point process phi, all the points in phi which have x coordinate between A and B and y coordinate anything, that will be counted. So how many points are there such that the x coordinate is between A comma B and the y coordinate is anything, like for example from -infinity to +infinity? That will be density into size of this. And the size of this set, this set recall in two dimension is a comma b cross r. Size of this set is infinite. So total number of points will be infinite. It's intuitive to think of, like if I ask like if the original point process, how many points have x coordinate between them, but the y coordinate can be anything. So all this is the equivalent region, which is like a strip, which have x coordinate between a and b, and y coordinate can be anything. So it's a vertical. It's a vertical strip between A comma B, and because it has infinite size, number of points in this size is infinite if the point process is uniform. Okay, so original point process is locally finite. Original point process is uniform, but the new point process, the derived one in the equivalent one in the one-dimensional marks, is not locally finite. Okay, now let's take a mark point process xi comma pi. with uniform density. So xi is uniformly, its density is uniform, and the pi is the power of denoting the transmit power of the ith point. Okay, and xi is a two-dimensional point. Now, if we combine them, we get a three-dimensional coordinate. So each point will be equivalent point in a three-dimensional space, and I can construct a new point process in three dimensions. So it's a 3D point process, phi dash, where each point is xi comma pi. Okay. So I may ask, how is this different than a 3D PPP, 3D point process? Okay. So first of all, phi dash is a point process with density lambda a, Ca, which cannot be uniform. Right? Why? Because if you so to see this, if there is a uniform 3D point process, then it should grow uniformly in all directions. So if I take a set of 0 comma a cross 0 comma a cross 0 comma 2h, the its size should be 2 times 0 comma a cross 0 comma a cross 0 comma h in the third dimension. Okay, but that is not the case with phi dash. Okay, because there are marks. So the maximum number of points, regardless of the mark. So if I take 0 comma a cross 0 comma a cross some set, then the maximum number of points depend on the first two coordinates. It will be lambda into a square. Okay, regardless of the mark. And if there are some mass restrictions, if the set is restricted, then the total number of points will be less than this. Okay, so it may happen that after it doesn't always increase in uniformly in the third dimension, which is the mark dimension. Okay, and it cannot be uniform in the mark dimension. Actually, you can see this. Let us consider a cylinder x square plus y square less than r square, and z belongs to r. Okay, so its base is a ball, a circle of radius r, and its z can be anything, any number. So this will be ball circle in the two dimension cross the real line in the third dimension. So a uniform 3D point process will have infinite points in it, okay? Because this is an infinite set. So if it's a uniform 3D point with some density lambda, then the total number of points will be infinite. Okay, while phi dash, which is the two-dimensional point process of base stations with the third dimension as the transmit power or the height or some mark, that if I ask you how many points are there, the total number of points would be depends only on the first two coordinates. So if I take a ball 0 comma r and there is no marks restriction, marks can be anything, the total number of points will be lambda into area of this ball, which is pi r square. So phi dash will have average lambda pi r square point, while a uniform 3D point will have infinite point. Okay, so this just tells that phi dash cannot be uniform in the or in both all three dimensions. Okay, a simple 3D point process will not have 2 points at the same 3D coordinates as same 3D coordinates, and a simple two-dimensional process with scalar mark will not have 2 points at the same 2D coordinates. Okay. So there are some differences, what you can expect, but nonetheless, you can always represent a PP in RDA plus S as a equivalent the point process in RD and the mark in R. Okay. And of course, it will be different. The difference is always there. For some finite set A in a D-dimensional space, phi 1 A cross RL, which denote number of points in A with mark RL, that will be equal to number of marks in set A, and that will be finite. Okay, but if there is a point process, uniform point process, then A cross RL is not infinite, so the number of points will also be infinite. The other difference would be if there is a point process in RD cross RL, if you shift a point, the shift occurs in all dimensions. Okay, so if there is a y vector from RD cross RL, if you shift the point process, it will become x minus y. While in a mark point process with point in RD and the mark in RL, if you shift it, you shift only the point coordinate and the mark will follow. So if there is a y coordinate in RD, then shifted version is defined as x minus y comma mi. So the marks are not shifted. The marks follows the point. The second difference is if the B is a bounded set in RD, then lambda B cross RL is infinite because the point process in the D plus L dimension. And the total set B cross RL is infinite. So if it's uniform, then it will be infinite. But Namar point process, only the first RD coordinates define the location of points. So B cross RL for this case means all the points which are in B and their mark are in RL. And because I am saying the mark is RL, which means that mark can take any value in the L dimension. So there is no restriction in mark. It is the same as saying how many points are there in the set. And that is finite and should be equal to lambda B. If the point process, of course, locally finite. Okay. Another example can be two-dimensional point process with height as mark versus three-dimensional point process. If I see the difference, so if I have a two-dimensional point process with height hi, I can add hi to the two first coordinates, and I get the three coordinates xi, yi, comma hi, which is in three dimension. So it's a point process in the three dimension. Okay. If you take a three-dimensional cube, which is defined as x, absolute value is x less than 1, absolute value y less than 1, and absolute value of h less than 1. This is a unit cube of two sides in all directions centered at the origin. Okay, and the base of this cube is a square, which is denoted as mod norm x is less than 1 and norm y is less than 1. Okay, and I is the height interval. So how many points are there inside this cube? So which means that if a point in three dimension, the equivalent three-dimensional point process, if it is in this square, then if it is in cube, it means x coordinate should be between -1 and 1, y coordinate should be -1 and 1, and height should be -1 and 1. So this means that the point coordinate should be in the square S, and its height, its mark, should be in the interval. Okay, so total number of points in this cube is cube can equivalently be written as S cross I. Okay, so that the how many points are there, that will give to a number of points. Okay, and the volume of C is infinite is still phi C. Yeah, sorry. If I take another cylinder where height can take any value, then what I am actually looking at a very long infinite height cylinder. Sorry, a net height cylinder with the square base, and the volume of C is infinite. The total number of points in this set is still finite because the point only grow in the first two coordinates. So, and that is a finite set. That's a square of radius, sorry, of size 2 cross 2. So number of points in that is finite. And because there is no restriction on height, it means all the points which fall in this square will be counted. Okay, but if I take the third as a sum set, then the number of points, we have to filter out those points which have mark in this interval, so it will be little less. Okay, so the number of points in C in this particular example would be just lambda into size of S. Okay, if this is a uniform point process. Before going further, I will define what is typical mark and typical point. So first, we are going to use this concept a lot in the research. So it's better to get it clear. Typical point is a point. Typical point of a point process is a point selected arbitrarily among all points of the process without any special consideration. Okay, so if there is a point process, you just pick one point randomly. Okay, and that will be a typical point. And but you cannot have any special consideration. For example, if you take the point closest to the origin, then you are having some bias that the point is close to the origin. So what is the bias there? It means if you suppose the point is at the r distance, if you create a ball of radius r, then there will not be any point in that. So the local neighborhood of that point is little bit different, right? So so local neighborhood of the closest point is a little bit different. So that is not a typical point. Typical point is which is just arbitrary and there's local environment and nobody it can be, which is just a typical representation of the point process. Okay, a point taken such that it always have a neighbor within 10 meters, that is also not a typical point because I'm taking some considerations. And what is typical mark? Now, once I have a typical mark, the typical point, the mark of that typical point is a known as typical mark. Okay, so many times people will ask you what is a typical mark distribution. It just means you pick a point randomly and then you ask its point. It asks its mark and find out which distribution. That is typical mark distribution. Okay, and it's equivalent to going to a random point and just ask what is the distribution of your mark. Okay, and sometime if you start stationary point process, the mark distribution may depend on the location. So given the point xi is located at coordinate x, okay, so xi is a random point here, and x is some fixed location. So given that there is a point, typical point is at coordinate x, the distribution of its mark is denoted as fx comma dm. Okay, and what is fx dm means the mark of the point xi lies in the set dm. So dm is a interval or a set subset in the mark space. So if mark is a scalar, dm is just a small interval. If mark is a two-dimensional point, then dm is a two-dimensional set. So given the point location is at x, distribution of this mark is denoted by fxd. Okay, which just means the probability that the mark lies in the set D. Now, given the point xi is x, the probability that the mark lies in the set k would be given as if I integrate this distribution. Okay, so in other words, it also means that probability m belongs to k given x is also noted at nu xk. Okay, and if you integrate the above distribution, then you should get this value. So you have to just take this mark distribution and integrate with respect to the mark set, subset to get the probability that the mark belongs to this set K given the point is at X. So palm distribution of mark is defined. So this we known as palm distribution. Palm distribution of mark at X is defined as distribution of mark Mx of the point X given that there is a point at X. So we condition that there is a point at X and whatever is the mark of this point we denote as Mx. The probability or the distribution of this mark is known as the palm distribution of mark at X. So in particular, we can say palm probability of K at X is defined as the probability that the mark X belongs to set K, given that there is a point at X. So this is denoted as this one. We put a X on top of P. So this means probability condition that there is a point at X. So always remember this superscript here in front of probability, which means that there is a conditioning that there is a point at X. So probability, there is a condition at X of the mark of that point X belongs to K is defined as probability that mark X belongs to K given X belongs to 5. There is a point in phi at x. So this we denote as the palm probability of k. Okay, and the distribution is generally known as the palm distribution. So if the point is at the origin, just a special case, then I will have O here, which is at origin. So that means the probability that there is a point at the origin and the probability of its mark. So M0 is the mark of the point at the origin belongs to K. Okay, so M0 is the point, MO is the point, mark of the point at origin belongs to K, given origin belongs to phi. So here the point at the origin represents a typical point if the point process is stationary. Okay. So if something is the point is stationary, you can take typical point anywhere. The location does not matter. Distribution will be the same. So you can just take the point at the origin. Okay. And for non-stationary parameter, that is not the case. So if I just talk about typical point can be anywhere, right? So you need to basically average out the distribution at different x to get the typical point distribution of marks. So let us come to the independent marks. A marking in a point process is said to be independent if for any point x1, m1 and x2, m2 both belongs to this point process, the distribution at f1 and m2 are independent. Okay, this just means that the distribution of one point's mark does not depend on the other point's mark, and distribution of m1 depends only on x1. It doesn't depend on any other point, location, or marks. Okay, so the independent marking means the mark of each point is independent of other points, location, and their mark. Okay, and a mark point process having independent mark is known as the independent mark point process. Okay, so what can be an example? Given a point process in RD, I assign an independent uniform random variable yi to each point, okay, to get a mark point process in RL cross R. So a marking which does not satisfy the above condition is dependent mark. Okay, so in this case, the mark may depend on the other point's location or the point's mark of the other points also. Okay, so what can be an example? Let's given a point process, define the mark of each point xi as mi is phi of bxi comma. So bxi comma is the ball around the point xi of radius r, and phi of the means how many points are there in this ball. Okay, so what I'm doing is for every point I am making a ball of radius r around itself, and then ask how many points are there, and whatever is the answer, that will be the mark of that point. Okay, so it is basically a total number of neighbors for each point. And that is a mark because it's a random variable. It depends on the points. So, but it will be dependent marks, right? So basically you can look at these are different points and this person makes a radius r and asks how many points are there in this ball around me. Okay. And if you go to another point, he will have the same question. He will construct a ball around himself and ask the same question. Okay. So is it clear that why it is dependent mark? Because if this person, suppose, does not have any point, right? Or suppose this person has only one neighbor, this one, suppose. And then, so this point will also have at least one neighbor that we know. So the distribution of mark has changed because of this point's distribution. Another example will be a set of blocks in a Minesweeper game, right? You must have played this. So in this game, you have points and then it denotes numbers in this around which may have mines. Okay, so if you can think of the mine number as a mark, these numbers are dependent. Okay, what can be another example? We define as generalized marks. So normally when I said the marks should be in a scalar or in a d-dimensional vector, but in general, you can extend this definition to say that the any function of point process is a random variable, so it can be the mark of point. Okay, So you have the marks are random variables, right? Or random variables or random vectors, anything. Okay, and because random variable means they are mapped from the sample space, and phi itself is a sample space mark, right? Sorry, phi itself is a map from the sample space. So you can map from the phi itself to get this random variable. So we can assign a function of point process as a mark of each point. Let's assume f is a function of, and f phi is a random variable or random vector, and mi is a mark of the ith point. Okay, and I'm assigning the same marks to every point. So the mark point process will be phi m xi comma f phi. Okay, f phi is a random variable which depends on the current realization, and I calculate this. So I have one realization. I calculate this function, and I assign that value to every point as a mark. Okay, this is a dependent marking because every point has the same mark, so they depend. And sometimes you can extend this definition to say that the whole phi can be assigned as a mark to each point. Similar to the stationarity in point process, we can also define stationarity in marked point process. Before that, first let us understand what is translation in a marked point process. Suppose there is a point process, marked point process xi comma mi. So xi is the point for the points, and mi are the marks, the corresponding marks. And if suppose there is a vector in the point space, then the shifted mark point process will be given by xi plus v comma mi. So what I'm doing is I'm taking each point from the original point process, and I'm shifting it by coordinate v. And note that the marks are not shifted, they just follow the point. So if a point moves from point A to point B after the shifting, the mark of the originally the point of point A will now become the mark of the point B. Okay. So a marked point process is said to be stationary if original point process and the shifted point process have the similar properties for all v. Okay. So law of phi plus v is equal to law of original point process. So this basically means that if you shift the point process, suppose there is a point at the origin, and that now shift. So if the mark is mj, now you shift the point, so the point shifted to 2, 3, and now its mark is still m0. So whatever is the distribution of m0, now that distribution will be seen if there is a point at 2, 3. Okay. Now if I compare with the original distribution, if there was point at 2, 3, its marks will have distribution of m2, 3. So if the translation does not change the distribution, it means the distribution of m0 should be equal to distribution of 2, 3. Okay, so marks distribution should not change on the location. That's the additional condition, and of course the original point process need to be stationary itself. So the translation of points should not change the distribution of the points. Okay, the stationary of MPP means the distribution of mark is identical across all points irrespective of the location of the point, and along with that the original point process need to be stationary. So if I want to say this, the underlying point process must be stationary. It means if you shift the points in point process, the distribution should remain the same. And the second is the mark of the point does not depend on the location of the point. The above two conditions ensure that if you shift the mark point process, the recomputed distribution of any property of point location and marks, we get the same distribution. So example whose mark depend on the location of xi. For each point, if I assign its distance from the origin as mark, h equal to s square plus y square. So it's a two-dimensional point process, and the mark of each point is x square plus y square, where x and y are the x and y axis coordinates. If there is a point z at the origin, the associated mark would be 0. When we shift the point, location of each point will change, but the mark must follow the point. So for the shifted point process, the point G is now at minus z actually. So Once again, yeah. So the point is at the origin. So when I shift by v, the point is now at minus v, and this mark is still 0. Okay, and if so, you can expect that there's a point at minus v and the mark is 0. And compared with the original point process, if there was a point at minus v, its marks would be now of v. So distribution has changed due to the shift, and hence the point process is not the stationary mark point process. Consider a point process where each point carry a ball. The color B of the ball at point X can be blue with the following property. If X belongs to ball at 0R, it has a 2 by 3 probability of blue. And if its X is outside this ball, then it has 0 probability of being blue. And otherwise it will be black. The point inside the ball has blue balls with probability 2 by 3 and the black ball with probability 1 by 3, and the ball outside ball always have a black. Okay, if you treat B as the mark of the point, the color of the ball is the mark of the point, this will not be a stationary point process. Because when we shift, there may be some point outside of ball 0R which will have blue balls because the mark will follow the points. And it is possible to have stationary mark point process with dependent marks. Okay, so there are two things: independent and dependent marks, and stationary non-stationary. They are not exactly related. They can be stationary mark point process with the dependent marks. Consider a mark point process where the mark of the point is given as the number of points in the ball of radius around the point x. Okay. So even if you shift it, the point will shift and the coordinate will shift. So if you create a ball around it, will still see the same type of distribution of the points around it. Okay. It's still possible to have non-stationary mark point process with dependent marks. So if you take number of points in the ball of radius norm xi at xi, then as you change the point, this ball radius will change. Okay, so the point which are closer to origin have a 0 radius ball, so there will not be any point in it. So the mark of the point at stationary is 0, while the points which are very far away, they have a larger radius, so they will have higher marks. So such as we have a intensity measure for the point process, we have a similar intensity measure for the mark point process, and we call it Campbell-Mathis measure. What it is basically a joint measure on the point process, point space, and the mark space. It is defined in the following way. Suppose there is a mark point process in RD cross RL. So points XI's are in RD and the marks MI's are in RL. In that case, the measure C hat A cross K is defined as A here is a subset of RD and K here is a subset of R. So this denotes some set of marks and this denotes some set of points. So the size of any set in RD cross RL is an expectation of this summation. So you go to each point in the point process and ask how many of you are in A and your mark is in K. Okay, so everyone will say yes, you count them. So you get a number of points which are where the point's location is in A and the mark is in set K. And then you take the expectation. So you can think that this is basically the expected number of points which lie in set A and has mark in the set K. Okay, so we will first define it for a stationary mark point process. For a stationary mark point process with intensity measure lambda A, so this intensity measure is the measure expected number of points in a set A without any marks consideration. So this is for the original point process. Now once we have marks, I will have a refined measure A cross K, which will tell me the number of points in A such that they have marks in K. Okay, so there will be of course less because I am of course counting some less marks, less points. I am excluding all the points which does not have mark in K. Okay, so this will be less than lambda A. So I do this. Now what I again understand is that this summation has this expectation with respect to number of points, locations, and the marks. So I can break this independence. What I do is I take the expectation respect to n outside, which is number of points. Then, so I have condition on that. I have expectation respect to xi, and because n is not deterministic, so this summation is has n summation. So this summation itself can be outside. Here you cannot take the summation outside expectation because you do not know how many terms are there. But once I condition an n, I know how many terms are there, so they become deterministic. So this summation term comes outside. Now there is expectation to xi's, all xi's. But this function is only a function of xi and mi. So I can just ignore other random variables and just compute expectation with respect to xi. So the expectation of xi, emi, and then condition m belongs to k, indicator xi belongs to a. Okay. Now if I have this measure, which is the distribution of the mark or condition on the point, so it says that it is the expectation of the distribution or the probability that the distribution belongs to k. Okay, so this is the palm distribution of the mark given the point location, and I do not include the point location because it's a stationary point process. So the mark distribution does not depend on the location, so I can avoid the location coordinate. So this mark distribution, no matter where the point is, that will be same. So let's assume the mark distribution is denoted by nu k, which is probability that mi belongs to k, which is the mark of a typical point. Okay, so when I look at this, I break this xi in emi. So this will be probability m belongs to k. So I will just replace nu k here. So this will become expectation is vector xi nu k xi belongs to a. Now this is constant, so it will just come outside. So vk, and this will come expectation that xi belongs to a. Okay, so this is nothing but the number of points in A. So this becomes nu k into lambda A. And of course, nu k is less than 1 because the probability distribution. So C A cross k would be less than lambda A. And if k is equal to RL, then nu k should be equal to 1. In that case, they are equal to 1. Which means that if I ask how many points are there which are in A and the marks in RL, okay, that just means total number of points in A because the mark in RL, because every point will have a mark in RL only. So that probability is 1. So what can be an example of this? Consider a Poisson point process in R square denoting the location of point xi, yi, and we assign height to each base station as transmitted as a mark. So now we will have a point process R in R square cross R. And these heights are independently assigned and uniformly distributed between 0 to 10 meters. So if I look at one typical base transmitter, it will have a height which is a uniform random variable between 0 to 10 meters, and it is independent of the others. Okay, so first I compute a distribution of this mark. Nu k is equal to probability m belongs to k is the integration over k of the distribution, the density probability density function of the mark. And probability density function of mark is 1 upon 10 indicator m belongs to 0 to 10. Okay, so this is the PDF of a uniform random variable between 0 to 10. Okay, and when you integrate it, this will become 1 upon 10, the size of k intersection 0 to 10. Okay, so whatever part of k is inside 0 to 10, the size of that divided by scaled by 10 will be the probability of this. Okay, so if I take k equal to RL, this will become 1. If I take k equal to 2 comma 3, this will become 2 comma 3 size, which is 1 by 10. So now the campus method measure will become lambda a into this measure. So it will be lambda 1 upon 10 into this size multiplied by the size of a. Okay. Because of stationarity, I have taken capital lambda a is equal to lambda into size of a. Okay, and this denotes the average number of base stations who lie in area A and have their height in the interval k. Okay, so if k is 0 to 1, 0, 1, which means all the base stations which has height less than 1, then the mean number of base stations in this area having height between 0 to 1 is lambda is suppose 20. Sorry, lambda a is 20, and then vk is 1 upon 10. So it will just become 2. There are 2 base stations which have height between 0 to 1. Okay, and total base station are 20. So out of 20, there are 2 base stations which have 0 to 1. Okay, and then so 1 upon 10 base station has this height, and that is intuitive because the mark distribution, probability that a typical transmitter will have height between 0 to 1 is 1 by 10. So I can also assign Campbell message measure for the non-stationary mark point process. So what will be different here is the mark distribution, because that will depend on the location x. So here I will have this new xk, which is the probability that the mark of a point at x belongs to k, condition that there is a point at x. This conditioning is always inherent, because without a point at x, we cannot define the mark at x. So for such point process, the underlying intensity measure is lambda A. C A cross K is equal to expectation over summation over indicator that point belongs to A and the mark belongs to K. Here I do the same thing. First condition on n and compute the expectation with respect to condition given n, and then I decondition with respect to n. So once I have this and conditioning, this becomes deterministic. So I pull the summation outside. Rest term is a function of points and mi's. So I condition on xi, right? So for every I will condition on a different point. So here I'm conditioning on xi, and then there will be expectation. This is a function of xi and mi. So once I condition on xi, the remaining randomness is respect to mi. So this will be expectation respect to mi given xi. Okay. So now this is not a function of mi, so it will come out. So only thing becomes this expectation of mi given xi, indicator of mi belongs to k. So this is nothing but the probability that mi belongs to k, condition on xi. Okay. So if the xi location is suppose at x, so this will be probability that m mark of point x belongs to k, given that there is a point at x. Okay. So let us denote by gxk. So gxk denote the probability that the mark of a point at x belongs to k, given that there is a point at x. Okay, and this is also equal to nu xk. We know that, right? But this is equal to mark distribution, which is can also be computed by integrating the marks probability mark distribution over set k. So once I have that gxk, so remember this term is defined this way. So if I have a point at xi, this will become gxi comma k. So I replace that here. So this become expectation with respect to xi, gxi comma k, indicator xi belongs to k. Okay. Now you look at this. This is a deterministic function f xi. Okay. So what I can do here is I have and again what I do is first I merge this expectation back. So and then conditional and there is xi. So the overall expectation is respect to phi, original phi. So I take this expectation to phi. I sum over all points in phi, and then I have this function as it is. Now this is a function of xi. So I can just write it like fi xi. Okay, this is no longer random. This is just it is no longer random on different marks or anything. This is just function on the point. So this is expectation of summation of functions. So I can apply Campbell theorem, normal Campbell theorem here, which will become the integration of lambda fx dx. Okay, or for non-stationary process, this will become fx into lambda dx. Okay, lambda dx. This is the measure that there is a how many points are there in the set dx. You multiply by this function and you integrate, you get a total summation over the points. Okay, so once I put this, what I get is that Campbell measure is integration of gx dx, and then gsk is nothing but integration of nu x dm over set k. Okay, so what I get is a double integration a cross k of nu x dm and lambda dx. So I take this product and integrate it. So from this, it is clear the density would be nu x in m into lambda x. So if I want to compute the Campbell sum of dx cross dm, it will be just new x dm into lambda dx. Okay. So this is the total number of points in small interval around x. And this is given that there is a point there, what is the mark distribution? Okay. So this is very intuitive to understand. So if I want to compute how many points are there which are around x and has mark in dm, what I do is I just calculate how many points are there. And because it is a small interval, all the point mark distribution is same. So I just compute that given that there is a point here, what is the probability that the mark will be in dm. And I take that probability and I multiply with the number of points. Okay, so if there are 10 points and there is a 1 by 10 probability that the mark will be in DM, then the probability would be just 10 into, sorry, there are 10 points and then there is a 1 by 10 probability that the mark will be in DM. So basically there will be on the average 1 point, which in this DX set, which will have a mark in DM, which will have its mark in DM.